The Big Bang theory suggests that the universe originated from a dense and hot point known as a singularity, where the density of energy and mass reached infinite levels, making traditional physical laws irrelevant. Albert Einstein's theory of relativity explains how mass can distort spacetime, affecting the flow of time. This theory also suggests that before the Big Bang is a meaningless concept, as the singularity's high mass would halt time. Evidence supporting the Big Bang theory includes the universe's expansion and the cosmic microwave background radiation, which originated about 379,000 years after the initial Big Bang event. The universe has evolved through various well-defined phases or epochs, such as the Planck epoch, Grand Unification epoch, Inflationary epoch, Electroweak epoch, Quark epoch, and Hadron epoch. These scientific explanations help to address deep questions about the universe. During the universe's diverse epochs, fundamental particles and forces underwent transformations to reach their current states, with quantum mechanics taking precedence over classical physics at immense scales. The application of quantum theory to the entire universe led to the development of inflationary quantum cosmology, offering an alternative view on the singularity. Quantum mechanics allows for particles to spontaneously appear from a vacuum, suggesting that the universe could have originated from a quantum fluctuation. Despite the theoretical idea of a vacuum as a state devoid of particles, the Heisenberg uncertainty principle introduces inherent limitations in measuring particle properties, leading to fundamental fuzziness at the quantum level. Einstein's equation E equals mc²2 suggests that the enormous positive energy in celestial bodies is counterbalanced by negative energy, potentially resulting in a net energy of zero for the universe as a whole. Stephen Hawking and physicist Alexander Vilenkin explored how a universe with zero total energy could emerge from a sustainable state of nothingness driven by cosmic inflation, creating a universe from a state where time is irrelevant. How does the universe create something from nothing? The quest to understand the universe inevitably leads to a series of ever-expanding questions about its origins and fundamental nature. Regardless of the specific subject of inquiry, the ultimate questions about the universe's inception and the emergence of something from nothing remain constant. Despite advances in science, these foundational questions persist. How did the initial conditions for everything we know come into existence? The ultimate question boils down to understanding how something could have originated from a state of nothingness. In scientific terms, the question of how the universe or the Big Bang emerged from a state of nothing remains one of the most profound and challenging questions. The inquiry not only seeks to understand the origins of all that exists, but also aims to comprehend the initial conditions that led to the universe's formation. Although scientific research has made significant strides, these fundamental questions about the universe's origins continue to elude complete understanding. Today's observations of the universe, accounting for known uncertainties, present a remarkably coherent picture. The universe consists of matter as opposed to antimatter, follows uniform physical laws across space and time, and originated from a hot Big Bang approximately 13.8 billion years ago. Governed by the principles of general relativity, the universe is in a state of expansion, cooling, and gravitational interaction. It is primarily composed of dark energy, making up 68%, and dark matter accounting for 27%, with the remaining components being ordinary matter, neutrinos, and radiation. Presently, the universe is populated with galaxies, stars, planets, heavy elements, and at least in one location, life forms with intelligence and technological capabilities. These complex structures did not always exist but emerged through cosmic evolution. Scientists in the 20th century made significant strides in outlining the timeline that explains how the universe transitioned from a homogeneous state, made solely of hydrogen and helium, to the complex, structure-rich universe we observe today. Starting from the present, we can trace back in time to inquire about the origins of each specific structure or component. For every answer obtained, the subsequent question becomes, where did that originate and how did it come into being? Until we reach a point where the only response is, we don't know, at least not yet. Finally, we can ponder what we do know and question. How did this come into existence? And is it possible that it emerged from nothing? The existence of life today is a result of complex molecules, which must have evolved from the atoms found in the periodic table. These atoms constitute the basic building blocks of all the ordinary matter in the universe as we know it. The universe did not come into existence with these atoms preformed. Rather, they were synthesized through multiple cycles of stellar birth and death. The byproducts of these nuclear reactions were then incorporated into subsequent generations of stars. Without this process, the formation of planets and complex chemistry would not be feasible. To form the stars and galaxies we observe today, several conditions must be met. Gravitational forces are needed to merge smaller galaxies and star clusters, thereby creating larger galaxies and initiating new cycles of star formation. This process requires the existence of pre-existing mass accumulations, which are formed through gravitational growth. These accumulations in turn necessitate the early formation of dark matter halos to prevent the newly formed stars from ejecting matter back into the intergalactic medium. An appropriate balance of ordinary matter, dark matter, and radiation is also needed to produce phenomena like the cosmic microwave background and the light elements that were synthesized in the hot Big Bang. Initial density variations, or C fluctuations, are required for these structures to grow gravitationally. Finally, mechanisms must exist for generating these density variations, as well as for creating dark matter and the initial amounts of ordinary matter. These conditions are critical in the early stages of the hot Big Bang to result in the universe as we know it today. Assuming that the laws of physics, space-time, and matter-energy also need to exist, these should be considered essential elements that must somehow come into existence. In summary, when considering whether a universe can originate from nothing, these are the yet-to-be-explained, novel factors that must somehow be generated. To understand why there is more matter than antimatter, it's necessary to look back to the early universe, a period when our understanding of physics is notably uncertain. The current laws of physics exhibit a kind of symmetry between matter and antimatter, meaning that every known reaction either creates or destroys matter and antimatter in equal quantities. However, the early universe, despite its hot and dense conditions conducive to the abundant creation of both matter and antimatter, must have had a mechanism to establish a matter-antimatter imbalance where none initially existed. Various methods could achieve this imbalance. While the exact mechanism in our young universe remains unknown, any viable approach would involve three key components: a set of conditions that are out of equilibrium, naturally occurring in an expanding and cooling universe, a means to facilitate interactions that violate baryon number, which the Standard Model permits through Sphalerine interactions, and a mechanism to produce sufficient C and CP violation to establish a significant matter-antimatter asymmetry. The Standard Model contains all these elements, albeit insufficiently. If one views a universe with a matter-antimatter symmetry as a universe from nothing, then it's highly likely that the universe did indeed generate something from nothing, although the precise mechanism remains uncertain. Similarly, there are several credible mechanisms for the formation of dark matter. Comprehensive testing and exploration have confirmed that dark matter cannot be composed of any particles that exist within the Standard Model. Its actual essence calls for an extension of physics beyond our current knowledge. Among the potential methods for its formation are its thermal generation in the early hot universe, which didn't fully annihilate and left behind stable particles such as the lightest supersymmetric or Kluzik-Klein particles. Another possibility is its emergence from a spontaneous phase transition as the universe expanded and cooled, extracting massive particles like actions from the quantum vacuum. It could also be a new form of neutrino that either blends with known neutrinos, referred to as a sterile neutrino, or exists as a heavy right-handed neutrino alongside conventional neutrinos. Alternatively, it could have originated as a purely gravitational phenomenon, resulting in the formation of an ultramassive particle like a Buguiam-Silo. The existence of dark matter in today's universe leads to the question of its necessity, especially when the early universe seemed to function well without it. A mechanism must have been in place to create this substance where it previously did not exist, and each of these scenarios requires energy. This naturally leads to the subsequent question: what is the origin of the cosmic inflation, which is the leading hypothesis for the origins of the universe prior to the Big Bang? The universe may have indeed originated from nothing. This concept requires some elaboration and is often what is meant by the phrase "a universe from nothing." When contemplating the initial phases of the hot Big Bang, one must consider conditions that were extremely hot, dense, high energy, and nearly uniform. When the question arises, how did this come to be, there are generally two avenues for explanation. One could assert that the universe was simply born this way. According to this perspective, the universe came into existence with these properties, referred to as initial conditions, and no further explanation is required. In theoretical physics, this approach is described as abandoning the quest for explanation. Alternatively, one could follow the typical approach of theoretical physicists, to devise a theoretical framework that could account for these initial conditions. This involves making specific predictions that diverge from those of the prevailing standard theory, followed by efforts to measure these critical parameters. The theory of cosmic inflation emerged from this second approach, fundamentally altering our understanding of how the universe came into existence. Rather than tracing hot and dense conditions back to an infinitely hot, infinitely dense singularity, the theory of inflation proposes that the hot Big Bang was preceded by a phase in which an exceedingly high energy density existed within the very fabric of space. This caused the universe to expand at an accelerating or inflationary rate. When this inflationary period concluded, the energy was converted into matter, antimatter, and radiation, resulting in what is observed as the hot Big Bang, essentially the aftermath of inflation. In more technical terms, this not only yields a universe with a uniform temperature, spatial flatness, and an absence of residual artifacts from a theoretical grand unified era, but also forecasts a specific kind and range of seed density fluctuations. These predictions were subsequently confirmed through observation. Thus, starting from what is essentially empty space, albeit space filled with a significant amount of field energy, a natural process has given rise to the entire observable universe, replete with complex structures as it is seen today. This concept of a universe emerging from nothing is the central tenet of the inflationary theory, although it doesn't satisfy everyone's quest for understanding. For a significant number of people, the idea of a universe where space-time, the laws of physics, fundamental constants, and some level of non-zero field energy still exist in the fabric of space is far removed from the concept of true nothingness. After all, it's possible to imagine a location that exists outside of space, a moment that is beyond the limits of time, and conditions that are not bound by any physical laws. These ideas, if seen as prerequisites for achieving a state of true nothingness, are philosophically valid. This underscores the difference between the philosophical concept of nothingness and its more physically based definition. There are 4 scientific ways to define nothing, each context-dependent. These include a moment when the subject of interest did not exist, a condition of empty physical space, a state of empty spacetime at its lowest energy level, and whatever remains after the entire universe and its governing laws are removed. If one uses the first 2 definitions, it's plausible to say that a universe could come from nothing. However, using the third definition makes this impossible, and with the fourth, due to a lack of sufficient knowledge, it's uncertain what the outcome would be. Without a physical theory to describe what exists beyond the universe and outside the existing physical laws, the concept of true nothingness remains undefined in physical terms. In the realm of physics, the concept of absolute nothingness is inherently problematic. What does it signify to exist beyond space and time, and how could space and time logically and predictably originate from a state of non-being? How can the emergence of space-time be pinpointed to a specific location or moment, when the very definitions of location and time depend on its existence? From where do the governing principles of quanta, encompassing both fields and particles, originate? This line of reasoning even presupposes that space, time, and the physical laws were not proofs depend on assumptions that have not been conclusively validated under the conditions to which they would be applied. If one adopts a physical interpretation of nothing, then it does appear that the universe as currently understood emerged from nothing. However, if one steps outside the bounds of physical limitations, certainty about our ultimate cosmic origins vanishes. Regrettably, the nature of cosmic inflation inherently eliminates any information that could be derived from a pre-existing state in our observable universe. Despite the boundless scope of human imagination, conclusions can only be drawn about subjects that can be tested within the framework of our physical reality. Regardless of the logical coherence of any other ideas, including the concept of absolute nothingness, they remain mental constructs. If the universe formed from nothing, who created the nothing? The cosmos, as we observe it now, is undoubtedly filled with matter. Everything we touch, see, and engage with is composed of minute particles at its core, and over the course of cosmic history, these particles have formed into vast structures like humans, celestial bodies, stars, galaxies, and clusters of galaxies, that all adhere to the same physical laws and are part of the same space-time continuum. Everything we witness and encounter in the cosmos has existed for only a limited period. There was a time when the universe lacked galaxies, stars, or even atoms, indicating they emerged at some juncture. But where did they originate? While it might seem intuitive to say from something, it's possible they came from nothing. In this context, how does a scientist define nothing? From a scientific viewpoint, there are four distinct interpretations to consider. The initial concept of nothing for scientists refers to a state where the essential components to produce your something were absent. Galaxies, stars, planets, and humans cannot exist without the necessary particles to construct them. Everything we are familiar with and engage with consists of subatomic material particles. These are the foundational elements that shape our universe as we perceive it. If we begin with a universe abundant in matter, we grasp how it can grow, cool down, and be influenced by gravity to evolve into the universe we recognize today. We comprehend the life cycle of stars, which results in the formation of heavier elements that pave the way for the birth of smaller stars, terrestrial planets, organic compounds, and ultimately, the potential for life. But the question arises, how did we end up with a universe dominated by matter and not one with balanced quantities of matter and antimatter? This represents the primary scientific interpretation of deriving something from nothing. It's a profound conundrum in physics. If the principles of physics dictate that matter and antimatter can only be produced in identical quantities, how did our universe evolve to be composed entirely of matter, with no trace of antimatter? Every celestial body, star, and galaxy we've observed is confirmed to be constituted of matter, not antimatter. So, how did we manage to have a surplus of these vital foundational elements if the universe didn't start with such a surplus? This is the essence of the statement that the matter in our universe emerged from nothingness. The mystery of why there's more matter than antimatter, a challenge referred to as baryogenesis within the physics realm, stands as one of the most perplexing unsolved questions in contemporary physics. Numerous theories and processes have been suggested, and while they seem theoretically feasible, the definitive answer remains elusive. We're still uncertain why there's an imbalance, more matter than antimatter, instead of a perfect balance, equal proportions, in the first place. The second interpretation of nothing for scientists is the emptiness of vast space. Maybe you lean towards a definition of nothing that genuinely encompasses no things whatsoever. If that's your perspective, then the first explanation falls short, since it undeniably contains something. To truly grasp the concept of nothingness, every basic element of matter must be eradicated. Every single radiation quantum must vanish. Every particle and antiparticle, from the elusive neutrino to the mysterious substance of dark matter, has to be eliminated. If you could manage to expel them all, without exception, what would remain is just the vast expanse of empty space. Devoid of particles or antiparticles, absent of matter or radiation, and lacking any discernible quanta in your universe, you'd be left with the genuine scientific meaning of nothingness. Yet, even in this highly constrained and imaginative setting, certain fundamental aspects persist. The foundational laws of physics remain intact, implying that quantum fields continue to pervade the universe. This encompasses the electromagnetic field, the gravitational field, the Higgs field, and fields associated with nuclear forces. Space-time remains, dictated by the principles of general relativity. All the essential constants are still present, retaining the values we've observed. And perhaps most crucially, the inherent energy of space, known as the zero-point energy, persists and maintains its current positive, non-zero magnitude. In the present day, this is evident as dark energy. Prior to the Big Bang, it was manifested as cosmic inflation, which culminated in the birth of the entire universe. This gives rise to the notion of a universe from nothing. Even in the absence of any form of matter or radiation, this version of nothing still results in a captivating universe. The third interpretation of nothing for scientists is the conceptualization of nothingness as the ultimate lowest energy state achievable for spacetime. Presently, our universe possesses a zero-point energy, a form of energy intrinsic to space, which holds a positive, non-zero value. We're uncertain if this represents the genuine base state of the universe, meaning the absolute minimum energy state, or if there's a possibility to descend even further. There's a chance we might be in what's termed a false vacuum state, with the genuine vacuum or the absolute lowest energy state either nearing zero or perhaps even reaching or surpassing it. Transitioning from our existing state to this potential state could trigger a cataclysmic event that reshapes the universe, a dreaded phenomenon termed vacuum decay. Such a transition would have dire consequences for our existence. Photons would acquire mass, the electromagnetic force would be confined to limited distances, and the majority of the sunlight from our sun would be obstructed from reaching Earth. Envisioning this as the epitome of genuine nothingness, it might be the perfect situation that preserves the laws of physics, albeit with some modifications. If one could attain the universe's true foundational state, whatever its nature, and purge all matter, energy, radiation, spacetime distortions, and fluctuations, what remains would be the pinnacle of material emptiness. There would still be a backdrop for the universe's events, but it would be devoid of actors. The play would lack characters, a storyline, and a setting, yet the expansive void of material emptiness would still offer a platform. The cosmic vacuum would be at its ultimate low, rendering it impossible to derive any work, energy, or tangible particles or antiparticles from it. However, for some, this scenario still resonates as something, given that the constructs of space, time, and governing principles remain intact. The fourth interpretation of nothing for scientists is the idea that true nothingness is achieved only when the entire universe and its governing laws are eradicated. This is the most radical notion, a perspective that ventures beyond the confines of reality, transcending space, time, and even the realm of physics, to envision an ultimate form of void. We can think of eliminating everything conceivable, the dimensions of space, the continuum of time, and the foundational principles that dictate reality. Within the domain of physics, there's no framework to define this. It represents an absolute philosophical void. From a physics standpoint, this poses a dilemma. Such a form of void is incomprehensible. We'd be forced to postulate the existence of a state that can prevail beyond the boundaries of space and time, and from this theoretical, perfect void, spacetime and the laws overseeing all known physical phenomena could potentially originate. Regrettably, we're uncertain if this train of thought holds any tangible significance. It might just be a testament to our ability to conceptualize scenarios beyond our tangible reality without any real-world relevance. Venturing down this path immediately presents a plethora of questions, all without clear resolutions. These questions encompass: how can spacetime manifest in a specific place or moment when concepts like space, for positioning, or time, for moments, don't exist? Is it even feasible to conceptualize something as external to the universe without space, or commencing without time? From what origin would the principles that dictate particle behaviors and their interactions emerge? This ultimate notion of nothingness, though it might resonate as the most philosophically complete, might lack any real essence. It might merely be a conceptual framework to shape the concept of nothing. They often miscommunicate, assuming their interpretation of nothing is the universally accepted one. However, there's no unanimous agreement. Words can be open to interpretation, and the notion of nothingness varies depending on the context and individual. The phrase "something from nothing" might refer to the emergence of a fundamental entity where none previously existed, but not all would concur that it sprouted from nothing. Each of the four outlined definitions holds its own merit, but it's crucial to discern the intended meaning when someone references their specific version of nothingness. Every definition has its distinct boundaries and applicability, relevant to various physical challenges, from the genesis of matter to the mysteries of dark energy, cosmic inflation, and the inherent energy of space. However, there's an inherent limitation. These ideas are all products of human cognition. Everything we're aware of undoubtedly originated from nothing. The challenge lies in deciphering the process. Why can't we see 95% of the universe? The elements we understand, like atoms, celestial bodies, and living things, comprise less than 5% of the universe we know. Around 25% is dark matter, and 70% is dark energy. Both are undetectable. This is odd, suggesting our lived experiences capture only a small part of the full reality. Yet, it's even more perplexing. We're largely uncertain about what dark matter and energy are, although we're fairly confident they're real. So what's known? Dark matter is essential for galaxies to form. When we analyzed the universe's structure, it became evident that there's an insufficient amount of regular matter. The gravitational force of visible matter isn't potent enough to create galaxies or complex systems. Stars would likely be dispersed randomly rather than forming galaxies. Thus, we're certain there's another component that neither emits nor reflects light. This dark matter can be indirectly observed. Areas with high concentrations bend light that passes close by, so we're sure it interacts with gravity. Currently, we have more hypotheses about what dark energy isn't than what it is. We know dark matter isn't just ordinary matter without stars, as it would emit detectable particles. It's not antimatter, as antimatter emits unique gamma rays when reacting with regular matter. It's also not black holes, compact objects that had a violent impact on their surroundings, while dark matter seems dispersed. Essentially, we're sure of a few things. Something exists. It interacts with gravity. There's a lot of it. Dark matter is likely a complex exotic particle that doesn't interact with light and matter in a way we understand. Dark energy is even more enigmatic. We can't detect it, measure it, or taste it. But its effects are clearly visible. In 1929, Edward Hubble studied how light wavelengths from distant galaxies shift towards the red end of the spectrum as they travel through space. He found that fainter, more distant galaxies showed more redshift. Closer ones, less so. Hubble concluded this was because the universe is expanding. The redshift happens because light wavelengths stretch as the universe expands. More recent findings indicate that the universe's expansion is accelerating. Previously, it was believed that gravity would slow down or even reverse this expansion. Space doesn't change its properties as it expands, there's just more of it. New space is constantly being created everywhere. Galaxies are tightly bound clusters held together by gravity, so we don't experience this expansion in our daily lives. But we see it everywhere. Wherever there's empty space in the universe, more is forming every second. So dark energy seems to be some kind of energy intrinsic to empty space. Energy that's stronger than anything else we know and keeps getting stronger. Empty space has more energy than everything else in the universe combined. We have multiple theories about what dark energy might be. One theory is that dark energy is not a thing but a property of space. Empty space isn't nothing. It has its own energy. It can generate more space and is quite active. So, as the universe expands, it could be that just more and more space appears, leading to a faster expanding universe. This theory is similar to an idea Einstein had in 1917, the concept of a cosmological constant, a force that counteracts gravity. The only issue is that when we tried to calculate this energy, the result was so incorrect and strange that it only added to the confusion. Another theory proposes that empty space is teeming with brief, virtual particles that continually pop in and out, adding to dark energy. Or maybe dark energy is an unknown kind of dynamic energy fluid or field that permeates the entire universe, but has effects contrary to those of we don't know how or where or how we could detect it. So there are still many questions to answer. Our theories about dark matter and dark energy are still just that, theories. On one hand, this is frustrating. On the other hand, this is frontier science, making it very exciting. It shows us that no matter how much we think we understand, we are still very much primates with advanced technology. on a small, fragile planet in space, looking at the sky and wondering how our universe functions. There is so much more to discover, and that's fantastic. How many galaxies are in the universe? Galaxies are massive assemblies of stars that fill the universe. Counting them presents a formidable challenge for several reasons. First, the sheer number of galaxies, which can run into the billions, makes the task arduous. Second, the limitations of observational equipment add another layer of complexity. For the best results, telescopes need a large aperture and should ideally be located above Earth's atmosphere to avoid optical distortions. One example that highlights these challenges is a composite image created from 10 years of photos taken by a space telescope. This image, known as the Extreme Deep Field (XDF), was generated from observations of a tiny patch of sky over a total of 50 days. To put its size in perspective, if one were to hold up a thumb at arm's length to cover the moon, the area of the sky covered by the XDF would be about the size of a pinhead. Despite its small size, the XDF revealed thousands of galaxies at various distances, making it one of the deepest views of the universe at that time. Given that such a small area of the sky contains thousands of galaxies, it's reasonable to speculate about the number of galaxies in the entire universe. Estimates generally range from 100 billion to 200 billion galaxies. The launch of more advanced space telescopes is expected to provide further insights into early galaxies in the universe. The space telescope that produced the XDF has been instrumental in estimating the number of galaxies. Initially launched with a flawed main mirror, the telescope was repaired and has undergone several upgrades. In one study, the telescope was pointed at what seemed to be an empty region of the sky for 10 days. The result was an image containing an estimated 3,000 faint galaxies. Subsequent upgrades to the telescope allowed for more in-depth studies. In one such study, an image known as the Ultra Deep Field revealed about 10,000 galaxies in a small area of the sky. Another study, using improved instruments, focused on a portion of the Ultra Deep Field and found approximately 5,500 galaxies, even in this narrower field of view. In summary, current estimates suggest there are around 100 billion galaxies in the universe, a number that could rise to about 200 billion as telescope technology improves. The method for making these estimates involves calculating the fraction of the sky observed and extrapolating this to the entire universe. The underlying assumption in these calculations is that the universe is uniform and lacks significant cosmic variance. This idea, known as the cosmological principle, has its origins in the general theory of relativity, which describes how gravity affects spacetime. The principle posits that, when viewed at a sufficiently large scale, the universe appears roughly the same in all directions. Support for the cosmological principle comes from observations of the cosmic microwave background, CMB, a form of radiation that dates back to the early universe. Instruments have shown that the CMB is nearly identical in every direction, supporting the idea that the universe is homogeneous and isotropic on large scales. The age of the universe, determined through observations of its expansion and the movement of galaxies away from Earth, is estimated to be around 13.82 billion years. As the universe continues to age and expand, galaxies will move further away from Earth, making them increasingly difficult to observe. Interestingly, the rate of the universe's expansion exceeds the speed of light, which doesn't violate the laws of physics as the expansion applies to the fabric of the universe itself, not to objects within it. The acceleration of the universe's expansion introduces the concept of the observable universe, which refers to the portion of the universe that can be seen from Earth. In a time frame of 1 to 2 trillion years, some galaxies will move beyond the reach of our observation. This doesn't imply that the observable universe is all that exists. It simply means that some regions will be unobservable due to the finite speed of light. Galaxies are not static, they undergo changes over time. For example, the Milky Way is on a collision course with the Andromeda Galaxy, and this merger is expected to occur in about 4 billion years. Following this, other galaxies in our local group are likely to merge as well. Future inhabitants of such a merged galaxy would find themselves in a much darker universe, devoid of evidence for the existence of other galaxies or cosmic expansion. Theories about the early universe suggest the possibility of multiple universes, each potentially having different rates of expansion, types of matter, and physical laws. These other universes could also contain galaxies, but this remains speculative as current observational methods cannot confirm their existence. Therefore, the actual number of galaxies could be much higher than current estimates if multiple universes exist. Advancements in telescope technology, such as the James Webb Space Telescope, are expected to refine our estimates of the number of galaxies. Current telescopes can observe galaxies that formed about 450 million years after the Big Bang. The James Webb Space Telescope is expected to look back as far as 200 million years after the Big Bang. However, the overall count of galaxies is not expected to change significantly, suggesting that the current estimate of around 200 billion galaxies in our observable universe is likely accurate. While counting galaxies is a fascinating endeavor, the primary focus of astronomers is to understand how galaxies reveal information about the formation of the universe. Galaxies serve as indicators of how matter in the universe is organized on a large scale. Advanced telescopes will allow for the study of the universe's earliest galaxies, thereby enhancing our understanding of how galaxies have evolved over time. This will include insights into the formation of elements heavier than hydrogen and the processes behind galaxy mergers. One of the key questions in astronomy concerns the role of dark matter in the formation of galaxies. Although most of the universe is made up of dark matter, constituting about 80% of its mass, it doesn't emit light or energy, making it invisible. Studies have indicated that there's more mass in galaxies than what can be observed. Computational models suggest that dark matter serves as a kind of scaffolding on which visible matter accumulates to form stars and galaxies. The James Webb Space Telescope is expected to provide more insights into this, thereby enriching our understanding of galaxy formation and, indirectly, our estimates of the number of galaxies. If the universe is expanding, where is the center? Galaxies are massive assemblies of stars that fill the universe. Counting them presents a formidable challenge for several reasons. First, the sheer number of galaxies, which can run into the billions, makes the task arduous. Second, the limitations of observational equipment add another layer of complexity. For the best results, telescopes need a large aperture and should ideally be located above Earth's atmosphere to avoid optical distortions. One example that highlights these challenges is a composite image created from 10 years of photos taken by a space telescope. This image, known as the Extreme Deep Field (XDF), was generated from observations of a tiny patch of sky over a total of 50 days. To put its size in perspective, if one were to hold up a thumb at arm's length to cover the moon, the area of the sky covered by the XDF would be about the size of a pinhead. Despite its small size, the XDF revealed thousands of galaxies at various distances, making it one of the deepest views of the universe at that time. Given that such a small area of the sky contains thousands of galaxies, it's reasonable to speculate about the number of galaxies in the entire universe. Estimates generally range from 100 billion to 200 billion galaxies. The launch of more advanced space telescopes is expected to provide further insights into early galaxies in the universe. The space telescope that produced the XDF has been instrumental in estimating the number of galaxies. Initially launched with a flawed main mirror, the telescope was repaired and has undergone several upgrades. In one study, the telescope was pointed at what seemed to be an empty region of the sky for 10 days. The result was an image containing an estimated 3,000 faint galaxies. Subsequent upgrades to the telescope allowed for more in-depth studies. In one such study, an image known as the ultra-deep field revealed about 10,000 galaxies using improved instruments, focused on a portion of the ultra-deep field and found approximately 5,500 galaxies, even in this narrower field of view. In summary, current estimates suggest there are around 100 billion galaxies in the universe, a number that could rise to about 200 billion as telescope technology improves. The method for making these estimates involves calculating the fraction of the sky observed and extrapolating this to the entire universe. The underlying assumption in these calculations is that the universe is uniform and lacks significant cosmic variance. This idea, known as the cosmological principle, has its origins in the general theory of relativity, which describes how gravity affects spacetime. The principle posits that, when viewed at a sufficiently large scale, the universe appears roughly the same in all directions. Support for the cosmological principle comes from observations of the cosmic microwave background, CMB, a form of radiation that dates back to the early universe. Instruments have shown that the CMB is nearly identical in every direction, supporting the idea that the universe is homogeneous and isotropic on large scales. The age of the universe, determined through observations of its expansion and the movement of galaxies away from Earth, is estimated to be around 13.82 billion years. As the universe continues to age and expand, galaxies will move further away from Earth, making them increasingly difficult to observe. Interestingly, the rate of the universe's expansion exceeds the speed of light, which doesn't violate the laws of physics as the expansion applies to the fabric of the universe itself, not to objects within it. The acceleration of the universe's expansion introduces the concept of the observable universe, which refers to the portion of the universe that can be seen from Earth. In a time frame of 1 to 2 trillion years, some galaxies will move beyond the reach of our observational capabilities. This limitation doesn't imply that the observable universe is all that exists. It simply means that some regions will be unobservable due to the finite speed of light. Galaxies are not static, they undergo changes over time. For example, the Milky Way is on a collision course with the Andromeda Galaxy, and this merger is expected to occur in about 4 billion years. Following this, other galaxies in our local group are likely to merge as well. Future inhabitants of such a merged galaxy would find themselves in a much darker universe, devoid of evidence for the existence of other galaxies or cosmic expansion. Theories about the early universe suggest the possibility of multiple universes, each potentially having different rates of expansion, types of matter, and physical laws. These other universes could also contain galaxies, but this remains speculative as current observational methods cannot confirm their existence. Therefore, the actual number of galaxies could be much higher than current estimates if multiple universes exist. Advancements in telescope technology, such as the James Webb Space Telescope, are expected to refine our estimates of the number of galaxies. Current telescopes can observe galaxies that formed about 450 million years after the Big Bang. The James Webb Space Telescope is expected to look back as far as 200 million years after the Big Bang. However, the overall count of galaxies is not expected to change significantly, suggesting that the current estimate of around 200 billion galaxies in our observable universe is likely accurate. While counting galaxies is a fascinating endeavor, the primary focus of astronomers is to understand how galaxies reveal information about the formation of the universe. Galaxies serve as indicators of how matter in the universe is organized on a large scale. Advanced telescopes will allow for the study of the universe's earliest galaxies, thereby enhancing our understanding of how galaxies have evolved over time. This will include insights into the formation of elements heavier than hydrogen and the processes behind galaxy mergers. One of the key questions in astronomy concerns the role of dark matter in the formation of galaxies. Although most of the universe is made up of dark matter, constituting about 80% of its mass, it doesn't emit light or energy, making it invisible. Studies have indicated that there's more mass in galaxies than what can be observed. Computational models suggest that dark matter serves as a kind of scaffolding on which visible matter accumulates to form stars and galaxies. The James Webb Space Telescope is expected to provide more insights into this, thereby enriching our understanding of galaxy formation, and indirectly relativity allows for the universe to have one of three shapes: flat like a sheet, spherical like a ball, or resembling a saddle. The universe's shape has profound implications for its ultimate fate, revealing insights about its past and future. The density of the universe and its rate of expansion determine if it's closed, open, or flat. About 2/3 of the universe is dark energy, just over a quarter is dark matter, and the rest is regular matter. If the universe's gravitational pull counterbalances its expansion, it takes a spherical shape, closed universe, while if it doesn't, it resembles a saddle, open universe. Scientific data suggests the most likely shape is flat, where the density is just right for the universe to expand without curving. This flatness isn't the 2D type we're familiar with, but rather can be understood through analogies and comparisons. The cosmic microwave background, CMB, provides significant hints about the universe's shape, with most measurements aligning with a flat universe. However, a 2019 study suggested a closed universe based on CMB measurements from a space observatory, creating debate within the scientific community. While such a finding could challenge established astronomical research, other CMB measurements align with a flat universe. The overwhelming evidence supports the hypothesis of a flat universe, with additional data consistently reinforcing this conclusion. One study suggesting a closed universe exhibits a potential statistical fluctuation, as combined datasets found no deviation from flatness. Although our observations are limited to the observable universe, the current evidence points to a flat three-dimensional space. Determining the universe's age relies on its current state of expansion and cooling, tracing back to the hot Big Bang phase and the cosmic distance ladder. The universe's age is calculated to be 13.81 billion years with a 99.1% level of confidence, a result supported by multiple lines of evidence. Additionally, understanding the life cycles of stars provides secondary validation, indicating an age range between 13 and 14 billion years, ruling out ages like 13.0 or 15.0 billion years. In our observable universe, the consensus is that the universe is 13.8 billion years old, determined through various scientific methods. However, it's important to consider the relative nature of time across different parts of the cosmos. When observing celestial bodies within our galaxy, most appear to be around the same age as Earth, with minor deviations due to the finite speed of light. Yet, as we observe galaxies further away, we glimpse into the past, seeing early formations with primarily hydrogen and helium, lacking elements essential for rocky planets and life. This exceptional perspective leads to the realization that each observer, regardless of their location in the universe, perceives a 13.8 billion-year-old universe. However, for entities moving at speeds approaching that of light, time dilation would lead to a considerably younger appearance for their surroundings. Despite this, the universal truth of 13.8 billion years since the Big Bang persists throughout the observable universe. The concept of time travel has fascinated people for ages, creating a complex issue within the realm of physics. The understanding of time is a fundamental aspect of our universe, shaped by Albert Einstein's theory of general relativity, which treats time as a dimension in four-dimensional spacetime. Regardless of the controversial debate on the nature of time, the theory of general relativity led to the discovery of time dilation, where motion can alter the passage of time, as exemplified by the twin paradox. Early theoretical constructs by physicists like W.J. van Stockham and mathematician Kurt Gödel explored the potential for time travel using massive rotating entities and a rotating universe, but current evidence suggests otherwise. The introduction of Kerr black holes and wormholes as potential pathways for time travel further expanded the discourse, with physicist Kip Thorne theorizing about the utilization of a black hole connected to a wormhole. However, while the theory presents intriguing concepts, the feasibility of time travel through these methods remains speculative. The concept of time travel through a wormhole involves the intriguing idea of time dilation, where the movable end age is significantly less than the stationary end. This creates a connection in spacetime, enabling travel between different points in time. While this theory presents a plausible scientific explanation for time travel, uncertainties about the existence of wormholes and negative energy, as well as the practical construction of such a setup, remain unresolved. Despite these challenges, the concept remains an intriguing possibility. Understanding the universe as a whole involves studying various parameters that offer insights into its composition. Both naturally found in the atmospheres of gas giants and their icy moons are also produced by life on Earth. Phosphine, in particular, has recently garnered attention as a potential biosignature after its detection in Venus' atmosphere. However, both these gases are present in very small amounts on Earth, posing a challenge for their detection in the atmospheres of distant exoplanets. Methane and carbon dioxide are also considered potential signs of life, especially when found together, due to their biological origins on Earth. Animals produce both gases, with methane arising from organic decomposition and digestion processes, and carbon dioxide being a product of respiration and oxygen-consuming organisms. Additionally, carbon dioxide plays a crucial role in maintaining stable temperatures on a planet. An imbalance in its concentration can lead to extreme climate conditions like a runaway greenhouse effect or glaciation. Lastly, the existence of chemical imbalances in an exoplanet's atmosphere could be indicative of life. Life disrupts chemical equilibrium by consuming certain substances and producing energy and other byproducts. This concept aligns with the ideas of planetary scientist James Lovelock, co-founder of the Gaia hypothesis. In his work, particularly The Greening of Mars, Lovelock posited that true chemical stability is typically found in lifeless systems or planets, using Mars as an example to illustrate this point. Another potential biosignature not mentioned by Barstow is hydrogen. Recent research from Cornell University has revealed that volcanic hydrogen in an exoplanet's atmosphere might extend the habitable zones of stars. Hydrogen gas acts as a natural greenhouse gas, and volcanic activity is considered a crucial factor in the development of life. Further research from the University of Cambridge has introduced the concept of Hycean planets, ocean planets with hydrogen-dominated atmospheres, as prime candidates in the search for extraterrestrial life. Despite these findings, the presence of these chemicals in an exoplanet's atmosphere should not be interpreted as conclusive evidence of life. Barstow emphasizes the complexity and meticulous nature of exoplanet research. She points out that accurately measuring the quantities of these gases is challenging, as their signals can overlap and require careful separation for analysis. She underscores that the James Webb Space Telescope is just beginning to reveal a vast new field of planetary atmospheres. Through this exploration, many pre-existing assumptions about exoplanets and their atmospheres are likely to be revised or even disproven. Is it only a matter of time before we find alien life? The pursuit of discovering extraterrestrial life has shifted from questioning its existence to pondering when it will be found, reflecting a significant change in the focus of modern astronomy. There is a growing optimism among scientists that signs of life on distant worlds could be detected possibly within our lifetimes, with some even suggesting it could happen in the next few years. This heightened anticipation is bolstered by recent developments and missions in space exploration. For instance, the James Webb Space Telescope has provided encouraging signs of what could potentially be life on an exoplanet. This telescope, along with other missions, marks a new era in the space race, one that is now centered around making what could be one of the greatest scientific discoveries. The vastness of the universe, with its seemingly infinite number of stars and planets, leads to the logical assumption that Earth might not be the only place with intelligent life. Today's advanced technology and exploration capabilities have brought humanity to a pivotal point, where answering the profound question of whether we are alone in the cosmos is more possible than ever. This current phase in space exploration goes beyond just exploring the unknown. It's also about the quest to find life beyond our planet in the expansive universe. Telescopes are now capable of analyzing the atmospheres of distant exoplanets, searching for chemicals that are typically produced by living organisms, suggesting that the universe might have a predetermined expiration date, possibly between 2.8 billion to 22 billion years from now. The urgency to understand its trajectory has never been more pressing. Some even posit that the final countdown towards its end might have already commenced. This leaves us with a profound question. What is the ultimate fate of our vast universe? Through the examination of ancient luminescence, researchers can observe the residual radiation from the Big Bang, commonly referred to as the cosmic microwave background. The special theory of relativity suggests that time is not absolute. The principle is that the quicker one travels, the more time seems to slow down from another's perspective. In a universe with galaxies that are expanding and stars and planets that are rotating, the perception of time is not consistent, making the past, present, and future subjective. Using this concept and information from studies on the cosmic background radiation, the estimated age of the universe has been determined to be approximately 13799 billion years. This estimation provides insights into the potential end of the universe. Let's take a closer look at three hypotheses on how this result could arise. The primary hypothesis suggests the universe will conclude in a big rip, when the force of its expansion surpasses its inherent gravitational pull. This event would dismantle galaxies, subsequently affecting black holes, stars, and even Earth itself. The Earth, along with all of humanity, might gradually degrade into radiation, implode, or be torn asunder as the universe's expansion intensifies. This would result in a universe dominated by isolated individual particles. Up until approximately 5 billion years ago, the universe expanded at a leisurely pace due to its dominant gravitational force. However, in more recent times, this expansion has quickened, with many pointing to dark energy as the cause. For the Big Rip scenario to play out, dark energy has to overpower gravity to an extent where it can disintegrate single atoms. A couple of years ago, Marcello Descanzi, a mathematics assistant professor at Vanderbilt University in Tennessee, alongside physics professors Thomas Keffart and Robert Scherer, formulated a fresh mathematical framework for the Big Rip. According to this model, the universe's expansion rate will ultimately reach infinity. While past models often overlook viscosity, Descanzi's theory emphasizes that it's the universe's viscosity that triggers its catastrophic end. His concept draws inspiration from ideas presented by French mathematician André Leclerc in the 1950s. Another hypothesis regarding the universe's eventual fate is termed the Big Crunch. Should the universe's matter not expand indefinitely and instead begin to diminish over time, gravitational forces could take precedence. This would lead the universe to contract, resulting in the collision of stars, planets, and entire galaxies. Essentially, the universe would implode upon itself. In simpler terms, if the universe's expansion decelerates and the events of the Big Bang unfold in reverse, all would collapse back into a single point. Scientists from Denmark have recently asserted that this phenomenon, termed a phase transition, might already be underway in our universe, essentially eroding the cosmos. A phase transition can be likened to the process when water becomes vapor. As per the Higgs theory, such a transition took place a mere 1/10 of a billionth of a second post the Big Bang, leading to a change in the structure of spacetime. During this shift, what was once a void became permeated with an unseen entity now termed the Higgs field. If a concentrated Higgs field is present, the scientists from the University of Southern Denmark posit that a bubble of this condition could manifest anywhere in the universe at any moment. Their calculations indicate that this bubble might then proliferate at light speed, occupying all of space and transitioning the current Higgs field into a different state. Quantum mechanics principles also hint that random particles can spontaneously emerge from a void, a phenomenon frequently observed in particle physics tests. Some theorize that dark energy might trigger such quantum fluctuations, potentially leading to a new Big Bang that concludes our current timeline and initiates a fresh one. Based on our present understanding of physics, this is considered the least probable of the proposed outcomes, yet it remains a topic of discussion. The third proposition suggests that the universe might conclude with a big freeze. Ironically, also termed heat death, this outcome is deemed the most probable based on our current understanding of physics and the universe.